On August 15, 1977, a volunteer astronomer named Jerry Amen was reviewing printouts from the Big Ear radio telescope in Ohio when he saw something that made him grab a red pen and scribble a single word in the margin. Wow. He had just detected a radio signal 72 seconds long, 30 times stronger than background noise, coming from the direction of the constellation Sagittarius. It had all the hallmarks of an artificial transmission. The frequency was eerily close to the hydrogen line, the exact wavelength that scientists had predicted alien civilizations would use to announce their presence. Because hydrogen is the most abundant element in the universe, and any sufficiently advanced species would know we'd be listening there. For a brief moment, it seemed like humanity had received its first message from another world. But here's the thing. That signal never repeated. Not once. Not in the 47 years since. We've aimed our most powerful telescopes back at that exact spot in the sky dozens of times, and there's been nothing but silence. Complete, absolute, utterly terrifying silence. And that silence, it turns out, might be trying to tell us something far more disturbing than any alien message ever could. Because when you actually sit down and do the math, when you calculate the sheer number of planets in the observable universe, the silence doesn't make any sense. None whatsoever. There are approximately 2 trillion galaxies in the observable universe. Let that number actually sink in for a moment. 2 trillion, not 2,000, not 2 million, 2 trillion galaxies, each containing hundreds of billions of stars. Conservative estimates put the total number of stars in the observable universe at around 200 billion trillion. That's a 2 with 23 zeros after it. And we now know from data collected by the Kepler Space Telescope and other surveys that planets are not rare cosmic accidents, but rather the default outcome of star formation. Current estimates suggest there are at least as many planets as there are stars, possibly more. Many of these planets orbit within their star's habitable zone, that Goldilocks region where temperatures allow liquid water to exist on a planet's surface. Kepler data indicates that roughly 20 to 50% of Sun-like stars host Earth-like planets in their habitable zones. If we apply even the most conservative estimate and say only 1% of stars have planets capable of supporting life as we know it, we're still talking about 2 billion trillion potential homes for life. That's 2,000 million planets. Surely, somewhere in that incomprehensibly vast cosmic ocean, someone else figured out how to build a radio telescope. Surely, someone else looked up at their night sky and wondered if they were alone. Surely, we should be detecting something. But we're not. The universe, as far as we can tell, is playing dead. This is what's known as the Fermi Paradox, named after physicist Enrico Fermi, who, during a casual lunch conversation in 1950, suddenly stopped mid-bite and asked his colleagues a question that still haunts astronomers today. Where is everybody? Fermi had been discussing reports of UFO sightings, which were particularly popular in the press at that time, and he started doing some back-of-the-envelope calculations about interstellar travel. He realized that even with relatively slow spacecraft, a civilization could colonize the entire Milky Way galaxy in just a few million years. That sounds like a long time to us, but it's actually a geological eye blink. Our galaxy is over 13 billion years old. If intelligent life were common, if civilizations arose with any regularity throughout galactic history, then someone should have colonized everything by now, including Earth. Someone should have built structures we could see. Someone should be broadcasting. Yet, when we look out into the cosmos with our radio telescopes, when we scan the skies for any sign of artificial activity, we find nothing. Just the hiss of cosmic background radiation and the natural radio emissions from stars and pulsars and quasars. No obviously artificial signals. No megastructures. No signs of cosmic engineering. Nothing that screams intelligent design in a way we can't explain away with natural phenomena. The silence is deafening, and it has been since we first started listening over 60 years ago. The modern search for extraterrestrial intelligence, known by the acronym SETI, began in earnest on April 8, 1960, when a young astronomer named Frank Drake pointed the Tatel radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. This was Project Ozma, named after the princess in L. Frank Baum's Oz books who lived in a distant land, and it represented humanity's first systematic attempt to detect radio transmissions from another civilization. Drake chose to listen at a frequency of 1420 megahertz, right around that hydrogen line I mentioned earlier, and for 6 hours a day over the course of several months, he listened. He heard nothing. But Drake wasn't discouraged. He knew the odds were long that he was essentially trying to win a cosmic lottery by checking just two numbers. So he formalized his thinking into what's now called the Drake equation, a mathematical framework for estimating the number of active, communicative, extraterrestrial civilizations in our galaxy. The equation goes like this. You start with the rate of star formation in the galaxy, then multiply by the fraction of stars that have planets, then the number of planets per star that could support life, then the fraction of those planets where life actually develops, then the fraction where life evolves intelligence, then the fraction that develops detectable technology, and finally the length of time such civilizations release detectable signals into space. When Drake first presented this equation at a meeting in Green Bank in 1961, the attendees tried plugging in what they considered reasonable estimates for each variable. Even with conservative numbers, they concluded there should be somewhere between 1,000 and 100 million communicative civilizations in our galaxy alone. Carl Sagan, who was present at that meeting, later used more optimistic values and arrived at a figure of 1 million civilizations. 1 million civilizations, just in the Milky Way. And yet, we've heard nothing. In the 6 decades since Project Ozma, SETI has expanded dramatically. We've searched thousands of star systems across multiple wavelengths. We've looked for optical pulses, laser flashes, infrared signatures. The Breakthrough Listen project, launched in 2015 with $100 million in funding from Russian billionaire Yuri Milner, is the most comprehensive search ever undertaken. It's surveying the 1 million nearest stars, the 100 nearest galaxies, and the entire galactic plane using some of the world's most powerful telescopes. They're collecting more data in a single day than all previous SETI searches combined collected in a year. They're looking for signals across billions of radio channels simultaneously, searching for patterns that couldn't possibly be natural, and they're finding nothing. Well, that's not entirely true. They're finding lots of interesting signals, but every single one, upon investigation, turns out to be human-made interference, signals from satellites, or perfectly explicable natural phenomena. The WOW signal remains the most compelling candidate for an artificial transmission, and even that is probably just an anomaly. A recent paper suggested it might have been caused by a passing comet or perhaps a magnetar flare amplified by a hydrogen cloud, though these explanations have their own problems. The point is, in over 60 years of searching, we have not found a single confirmed technosignature. Not one verified artificial signal from beyond Earth. This absence is so glaring that some scientists have started to wonder if we're asking the wrong question. Maybe the issue isn't where is everybody, but rather, why is nobody broadcasting? Or worse, why is nobody left to broadcast? When the Drake equation was first formulated, there was genuine optimism in the scientific community that we'd detect alien signals within a generation. Frank Drake himself thought we'd find something by the year 2000. Carl Sagan publicly stated he believed the odds of M13, a globular cluster he once targeted with a radio message, harboring alien life were about 50-50. Astronomer Jill Tarter, who spent decades leading SETI research and was the inspiration for the protagonist in Carl Sagan's novel Contact, once said she expected to detect a signal during her career. She retired in 2012 without having found one. The optimism of the 60s and 70s has been steadily replaced by a more sobering realization. If they're out there, they're either very far away, very quiet, or very dead. The universe is under no obligation to make sense to us, of course. Our expectations, our assumptions about how common intelligent life should be, might simply be wrong. But that raises an uncomfortable question. What if the reason we haven't heard anything is because there's nothing to hear? What if the Great Silence, as it's come to be called, isn't a temporary situation that will be resolved once our technology improves, but rather a fundamental characteristic of the universe itself? What if we really are alone, not just in our galaxy, but in the entire observable universe? Before you dismiss that possibility as absurdly improbable, consider this. The fact that we exist, that we're here to even ask these questions, creates a massive observational bias. We can only observe a universe capable of producing observers. This is called the anthropic principle, and it's a bit of a mind-bender. Imagine a lottery with a trillion tickets. The odds of any particular ticket winning are effectively zero, essentially impossible. But someone has to win, and when they do win, they might look at their winning ticket and think, "Wow, what were the odds?" But the odds were always 100% that someone, somewhere, would win. They just happened to be the lucky one. We might be the cosmic lottery winners. Not because Earth is special in any designed sense, but simply because among the incomprehensible number of planets in the universe, some of them had to get lucky. And, by definition, we can only observe the universe from the perspective of a lucky planet because unlucky planets don't produce observers. This doesn't prove we're alone, of course. There could be millions of other lottery winners scattered across the cosmos, but it does mean that our existence tells us absolutely nothing about how common life is. We could be one of billions of civilizations, or we could be the only one, and our mere presence here doesn't help us distinguish between those possibilities. What does help us distinguish between them is observation. And that's why the silence is so significant. It's not just that we haven't found aliens. It's that we haven't found any evidence of aliens ever having existed anywhere we can see. We're not detecting megastructures. We're not seeing signs of stellar engineering, like Dyson spheres, partially enclosing stars to harvest their energy. We're not noticing unusual spectral signatures that might indicate industrial pollution in exoplanet atmospheres. We're not finding any of the things that a galaxy teeming with technological civilizations should theoretically produce. The Allen Telescope Array in Northern California, funded in part by Microsoft co-founder Paul Allen, consists of 42 radio dishes working in concert to scan the skies continuously. It's specifically designed for SETI research and has been operating since 2007. It monitors millions of frequency channels simultaneously and can observe multiple star systems at once. It represents exactly the kind of sophisticated, dedicated SETI infrastructure that early pioneers like Frank Drake dreamed about. And it hears nothing but silence. The problem is, our current technology is actually quite good at detecting certain types of alien signals, assuming they exist. If a civilization on a planet orbiting Proxima Centauri, our nearest stellar neighbor at just over 4 light-years away, were broadcasting radio signals with the same power as our most powerful radar installations, we could detect them. Not easily, mind you. It would take dedicated observation time and some luck with timing, but it's within our capabilities. And Proxima Centauri is one star. There are roughly 400 billion stars in the Milky Way. If even a tiny fraction of them hosted broadcasting civilizations, if even 1 in a million stars had a technological species transmitting radio signals, we should be detecting thousands of them. But we're detecting 0. This brings us back to the Fermi Paradox, which isn't really a paradox in the logical sense, but rather a profound contradiction between our statistical expectations and our observational reality. Various explanations have been proposed over the decades, and they fall into roughly 3 categories. First, they're out there, but we can't detect them yet. Maybe alien civilizations use communication technologies we haven't invented yet. Maybe they've moved beyond radio waves to quantum entanglement communication or something even more exotic. Maybe they're deliberately staying quiet, either out of fear or as a precautionary principle, essentially the same debate humans are having about METI, messaging extraterrestrial intelligence. Maybe they're so far away that their signals haven't reached us yet, or have become too weak to detect. This is the optimistic interpretation, and it can't be ruled out, but it requires a lot of maybes. Second, they existed, but they're gone now. Maybe intelligent civilizations do arise regularly throughout the galaxy, but they inevitably destroy themselves before they can spread to the stars. Maybe there's something about intelligence, about the development of advanced technology, that contains the seeds of self-destruction. Nuclear war, climate catastrophe, artificial intelligence gone wrong, engineered pandemics. Maybe every civilization faces these existential threats, and maybe most of them fail to navigate through them successfully. This is the pessimistic interpretation, and it has some rather disturbing implications for our own future. Third, they never existed in the first place. Maybe intelligence is so absurdly rare that despite the trillions upon trillions of planets out there, we might genuinely be the first and only species to develop technology. Maybe the path from chemistry to consciousness is so narrow, so fraught with evolutionary bottlenecks and planetary disasters and sheer bad luck, that it almost never happens. Maybe we're not just lucky. Maybe we're the jackpot. This is the lonely interpretation, and it's the one we're going to explore in depth, because the more we learn about biology and planetary science and evolutionary history, the more plausible it becomes, and the more terrifying. To understand why we might be alone, we need to understand just how hard it is to go from a sterile ball of rock to a species capable of contemplating its place in the cosmos. We need to trace the path that life took on Earth and identify all the places where things could have gone differently, where one cosmic dice roll landing the wrong way could have meant that this planet, this pale blue dot, would be just as silent and lifeless as everywhere else appears to be. We need to examine what scientists call the Great Filter. The story of why we might be alone in the universe begins 4.5 billion years ago, with a cloud of gas and dust collapsing under its own gravity. This wasn't special. Star formation is happening constantly throughout the universe. But what happened next, the specific sequence of events that led to Earth becoming a cradle for life, that might be special. That might be so statistically improbable that it almost never happens twice. Let's start with location, because in real estate and in astrobiology, location is everything. Our Sun formed in what astronomers call the galactic habitable zone, a relatively narrow ring within the Milky Way where conditions are just right for complex life to develop. Move too close to the galactic center and you're in trouble. The core of our galaxy is a violent place densely packed with stars, pulsing with radiation from the supermassive black hole at its heart. Stars there pass close to each other regularly, their gravitational interactions flinging planets out of stable orbits. Supernovae explode with alarming frequency, bathing nearby star systems in lethal doses of gamma rays and cosmic rays. Any planet unlucky enough to be in the inner galaxy would be sterilized repeatedly, its atmosphere stripped away, its surface scoured clean of organic molecules. Life might start there, but it wouldn't last long enough to evolve into anything complex. Move too far from the galactic center, out into the sparse outer regions, and you have a different problem. The stars out there formed from gas clouds that contained very few heavy elements. And by heavy elements, astronomers mean anything heavier than helium. Everything from carbon and oxygen to iron and uranium. These elements, the building blocks of planets and life, are forged inside stars and scattered into space when those stars die. The universe started with only hydrogen and helium. Everything else had to be manufactured through stellar nucleosynthesis and distributed through supernovae. Stars in the galactic outskirts formed before enough stellar generations had lived and died to pollute the interstellar medium with sufficient quantities of heavy elements. Without those elements, you can't form rocky planets. You can't form complex molecules. You can't form life as we know it. Earth formed in the sweet spot, about 26,000 light-years from the galactic center, far enough to avoid the chaos of the core, but close enough that our region of space has been enriched with heavy elements from countless previous generations of stars. But even within the galactic habitable zone, most star systems are uninhabitable for other reasons. About half of all stars are members of binary or multiple star systems, orbiting each other in intricate gravitational dances. Planets in such systems, if they can form at all, tend to have wildly unstable orbits. They might be ejected from the system entirely, or they might experience extreme climate variations as they're passed back and forth between stellar companions, baking during close approaches, and freezing when flung outward. A planet needs stable conditions for billions of years to give evolution time to work. Binary stars don't provide that stability. Our Sun is a solitary star, or at least it doesn't have any stellar companions close enough to disrupt planetary orbits. That's already cutting our habitable candidates in half. Then there's the star itself. Our Sun is what astronomers classify as a G-type main sequence star, right in the middle of the stellar mass range. This matters enormously. Massive stars, the blue giants and supergiants, burn through their nuclear fuel in just a few million years. That's not enough time. Life on Earth took about 1 billion years just to get from chemistry to the first single-celled organisms. It took another 2 billion years to develop complex cells, another billion to reach multicellular organisms, another 500 million to reach intelligent life. You need a star that's going to stick around for billions of years, providing steady energy output while life slowly, painstakingly, figures out how to exist. But you also can't go too small. Red dwarf stars, the most common type of star in the galaxy, accounting for about 75% of all stars, have their own problems. They're dim and cool, which means their habitable zones are very close to the star. A planet in the habitable zone of a red dwarf might orbit at a distance closer than Mercury orbits our Sun, completing a full orbit in just a few days. At that distance, the planet almost certainly becomes tidally locked, with one hemisphere perpetually facing the star and the other facing eternal darkness. One side bakes, the other freezes, and the temperature gradient drives ferocious winds. Even worse, red dwarfs are temperamental. They produce frequent and powerful stellar flares, especially when they're young, bombarding nearby planets with radiation. A planet close enough to be in the habitable zone is close enough to have its atmosphere stripped away by these flares. Even if life managed to gain a foothold, it would be repeatedly sterilized by bursts of X-rays and ultraviolet radiation. There are approximately 400 billion stars in the Milky Way. About 300 billion of them are red dwarfs. They're out. Another 100 billion or so are massive stars that burn out too quickly. They're out. About half of what's left are in binary or multiple star systems with unstable planetary orbits. They're out. Suddenly, the number of potentially habitable star systems in our galaxy has shrunk from hundreds of billions to maybe a few billion. And we're just getting started with the filters. Let's say you've got a nice, stable, sun-like star in the galactic habitable zone. Now you need to form planets, which sounds straightforward, but it's actually a chaotic mess. When a star forms, it's surrounded by a disk of leftover gas and dust. Over time, dust grains stick together through electrostatic forces, forming pebbles. Pebbles collide and stick, forming boulders. Boulders collide and stick, forming planetesimals, objects roughly the size of asteroids. And then things get violent. Planetesimals, now massive enough to have significant gravity, start smashing into each other at tremendous speeds. Most of these collisions are destructive, shattering the objects into fragments. But occasionally, two planetesimals hit at just the right angle and speed to merge rather than shatter. Over millions of years, a few lucky planetesimals grow by accumulating material, eventually becoming planetary embryos, objects roughly the size of Mars. These embryos then engage in a final phase of giant impacts, crashing into each other to form full-sized planets. This process is so chaotic that computer simulations produce wildly different outcomes every time. Change the initial conditions slightly, the starting positions of embryos or their velocities, and you get completely different final planetary systems. Sometimes you end up with several rocky planets in stable orbits. Sometimes everything crashes into the star. Sometimes planets are ejected from the system entirely, flung into interstellar space to wander the galaxy as rogue planets, dark and frozen. Earth got lucky. We formed at the right distance from the Sun, about 150 million kilometers, in what would later be recognized as the habitable zone. But we weren't alone. Current models suggest that the early solar system was much more crowded than it is today. There might have been dozens of planetary embryos careening around in the region where the inner planets now reside. Most of them didn't make it. They were destroyed in collisions or gravitationally scattered into the Sun or flung out of the solar system entirely. The fact that we're here, that Earth survived that violent phase of planetary formation, is the first piece of luck. But location isn't everything. You also need the right composition. Earth is a rocky planet composed primarily of iron, silicon, oxygen, magnesium, and other heavy elements. That might sound obvious, but it's not guaranteed. Jupiter and Saturn, the gas giants, are composed mostly of hydrogen and helium. If Earth had formed a bit farther from the Sun, in a region where ice could remain solid, we might have accreted a thick envelope of hydrogen and helium gas and become a mini-gas giant ourselves, completely uninhabitable. The composition of a planet depends on the composition of the protoplanetary disk it formed from, and that composition varies depending on the metallicity of the parent star. Stars with low metallicity can't form rocky planets. They might form gas giants, but without sufficient heavy elements, there's no material to build Earths. Our Sun has a metallicity right around the solar neighborhood average. Not too high, not too low. Lucky again. Now, let's talk about water, because life as we know it absolutely requires liquid water. Water is the universal solvent. It's the medium in which biochemistry happens. You need a lot of it, and you need it to remain liquid for billions of years. Earth's water is a bit of a mystery. We're not entirely sure where it all came from. The inner solar system, where Earth formed, was too hot for water ice to remain solid. Any water that was present would have been in the form of vapor, which would have been blown away by the intense solar wind from the young sun. The leading theory is that Earth's water was delivered later, after the planet had mostly formed and cooled down, by asteroids and comets from the outer solar system. These icy bodies, perturbed in their orbits by the gravitational influence of Jupiter and the other giant planets, rained down on the inner solar system during a period called the Late Heavy Bombardment, about 4 billion years ago. If this theory is correct, and the timing and quantity of water delivery were different, Earth could have ended up as a desert world like Mars, with only trace amounts of water locked in polar ice caps. Or we could have ended up as a water world, completely covered by a global ocean kilometers deep with no exposed land. Either scenario would make the evolution of complex life far more difficult. Desert worlds lack the surface water necessary for widespread biology. Water worlds lack the land-ocean interfaces where many crucial evolutionary innovations occurred, and they lack the exposed rock necessary for long-term climate regulation through the carbon cycle. Earth ended up with just the right amount of water, enough to cover about 70% of the surface, but leaving 30% as exposed continents. Lucky. But even having liquid water isn't enough if your planet can't hold on to it. This is where planetary mass becomes critical. A planet's gravity determines whether it can retain an atmosphere. Too small, like Mars, which is only about 11% the mass of Earth, and atmospheric gases gradually escape into space. Mars once had a thicker atmosphere and liquid water on its surface. We know this because we can see ancient river valleys and lake beds carved into its surface. But over billions of years, Mars lost most of its atmosphere. Solar wind particles, no longer deflected by a magnetic field after Mars's core cooled and its dynamo shut down, gradually stripped away the Martian atmosphere. Today, Mars has an atmospheric pressure less than 1% that of Earth's. Water can't remain liquid on the surface. It either freezes or sublimates directly into vapor. Too large, and you run into a different problem. Super-Earths, rocky planets with masses several times that of Earth, can retain thick atmospheres dominated by hydrogen and helium, left over from the protoplanetary disk. These atmospheres can be thousands of kilometers thick, creating crushing surface pressures and temperatures. Any water on the surface would be in exotic high-pressure phases, not the liquid water that life needs. Earth's mass is, once again, just right. About 6 times 10 to the 24th kilograms. Massive enough to hold on to a substantial atmosphere, but not so massive that we retained a crushing hydrogen envelope. Lucky. And then there's the magnetic field. Earth's core is composed of a solid iron inner core surrounded by a liquid iron outer core. The rotation of the planet and convection currents in the liquid outer core create a magnetic dynamo, generating a powerful magnetic field that extends tens of thousands of kilometers into space. This magnetic field, the magnetosphere, acts as a shield, deflecting the solar wind and preventing it from stripping away our atmosphere. Mars, as I mentioned, lost its magnetic field early in its history when its smaller core cooled and solidified. Without that protection, it lost its atmosphere and its water. Venus, which is nearly the same size as Earth, appears to have never developed a strong magnetic field, possibly because it rotates so slowly that no dynamo could be sustained. The lack of a magnetic field, combined with Venus's proximity to the Sun, may have contributed to a runaway greenhouse effect that turned Venus into the hellscape it is today, with surface temperatures hot enough to melt lead. Earth's magnetic field is powered by heat left over from the planet's formation and by the decay of radioactive elements in the core. We don't fully understand why Earth has such a robust magnetic field while Venus doesn't, given their similar sizes. It might have to do with the specifics of planetary composition, or the violence of Earth's formation, or just random chance. Whatever the reason, we have a magnetic field, and it's been protecting us for billions of years. Lucky. Now, let's talk about the Moon. Our Moon is enormous, the 5th largest moon in the solar system despite Earth being only the 5th largest planet. The ratio of the Moon's mass to Earth's mass is far higher than for any other planet-moon system in the solar system, except for Pluto and Charon, which are more properly thought of as a binary dwarf planet system. The Moon is so large that its formation requires a special explanation. The leading theory, supported by computer simulations and isotopic analysis of lunar rocks, is the giant impact hypothesis. About 4.5 billion years ago, shortly after Earth formed, a Mars-sized planetary embryo, sometimes called Theia, collided with the proto-Earth at an oblique angle. The impact was cataclysmic. It vaporized Theia and a significant portion of Earth's mantle, ejecting an enormous amount of material into orbit. This debris, still molten, gradually coalesced over thousands of years to form the Moon. This impact had several crucial consequences for the eventual emergence of life. First, it completely melted and homogenized Earth's mantle, helping to establish the plate tectonics that would later prove essential for long-term habitability. Second, it increased Earth's rotation rate. The day immediately after the impact was only about 5 hours long. This rapid rotation strengthened the magnetic field dynamo. Third, and most importantly, it gave us the Moon. The Moon's gravitational pull stabilizes Earth's axial tilt, the angle between Earth's rotational axis and the plane of its orbit around the Sun. Earth's axial tilt is currently about 23.5 degrees, and it's responsible for our seasons. But without the Moon's stabilizing influence, Earth's axial tilt would vary chaotically over millions of years, driven by gravitational perturbations from Jupiter and the other planets. Mars, which lacks a large moon, has an axial tilt that varies between 10 and 60 degrees over timescales of millions of years. When Mars's tilt is low, its poles point almost perpendicular to the Sun, and the polar ice caps expand to cover much of the planet. When the tilt is high, the poles point nearly toward the Sun, the ice caps sublimate, and Mars experiences extreme climate swings. Earth's axial tilt, stabilized by the Moon, varies by only about 2 degrees over 40,000 years. This stability has been crucial for the development of life. Complex organisms, especially large multicellular creatures, are sensitive to environmental conditions. They can adapt to seasonal variations, but they can't easily adapt to the kind of chaotic climate swings that Mars experiences. The Moon gave Earth climate stability for billions of years. The odds of a planet experiencing a giant impact at just the right angle and speed to produce a large stabilizing moon are not good. Computer simulations suggest that such impacts are rare outcomes of the planetary formation process. Most planetary embryos either miss each other entirely, collide head-on, and merge without ejecting enough material to form a moon, or collide at such high speeds that they shatter. Earth got lucky. Again, we're starting to see a pattern here. Now let's talk about Jupiter, because Jupiter might be the most important planet in the solar system for the existence of life on Earth, despite being hundreds of millions of kilometers away. Jupiter is enormous, 318 times the mass of Earth, more massive than all the other planets combined. It formed early in the solar system's history, within the first few million years, while the protoplanetary disk was still full of gas. Once it reached a critical mass, Jupiter's gravity was strong enough to start accreting hydrogen and helium gas directly from the disk, ballooning into the gas giant we see today. Jupiter's immense mass has profound effects on the rest of the solar system. Its gravity dominates the outer solar system, sculpting the asteroid belt between Mars and Jupiter, clearing out the Kuiper belt beyond Neptune, and, most importantly, acting as a cosmic vacuum cleaner for the inner solar system. Here's how that works. Beyond Neptune lies a vast reservoir of icy bodies, leftover debris from the formation of the solar system. These objects, comets, occasionally get perturbed in their orbits and fall inward toward the Sun. If one of these comets passes near Jupiter, Jupiter's gravity can do one of two things. It can slingshot the comet back out to the edges of the solar system, ejecting it entirely, or it can capture the comet, pulling it into an orbit that ends with the comet crashing into Jupiter itself. In July 1994, Astronomers watched as fragments of Comet Shoemaker-Levy 9 slammed into Jupiter over the course of several days. The impacts released energy equivalent to millions of nuclear weapons. If those comet fragments had hit Earth instead, they would have caused a mass extinction event, possibly the end of all complex life. Jupiter takes these bullets for us. Computer simulations of solar systems without a Jupiter-like planet show that rocky planets in the habitable zone get hit by comets far more frequently, perhaps 10 to 100 times more often than Earth does. Each impact is potentially sterilizing, resetting the evolutionary clock back to zero. The dinosaurs were wiped out by an asteroid impact 66 million years ago, and that asteroid was only about 10 kilometers across. Comets can be much larger, and they hit at much higher speeds. Without Jupiter, Earth might have been hit by extinction-level impactors so frequently that complex life never had time to recover and diversify. Intelligence requires time. Lots of time. You need long periods of relative stability for evolution to explore different solutions to the problem of survival. Jupiter gave us that stability. But here's the thing. Jupiter's existence and its specific location in the solar system are not guaranteed outcomes of planet formation. In fact, most of the exoplanetary systems we've discovered look nothing like our solar system. Many of them have hot Jupiters, gas giants that somehow migrated inward from where they formed, ending up in tight orbits around their parent stars, sometimes closer than Mercury is to the Sun. These hot Jupiters would have plowed through the inner solar system during their migration, ejecting or destroying any rocky planets in their path. Our Jupiter stayed put. It formed in the outer solar system and, apart from some possible small-scale migration early on, remained there. If Jupiter had migrated inward, there would be no Earth. If Jupiter had never formed at all, Earth would be bombarded constantly. The fact that we have a Jupiter-like planet at a Jupiter-like distance is, yet again, lucky. I want to take a moment here to emphasize what we're doing. We're not cherry-picking special features of Earth and declaring them all necessary for life. We're identifying conditions that were necessary for life as it developed on Earth. It's possible that life could develop under very different conditions, that our assumptions about habitability are too narrow. But we only have one example of life to study, and that's life on Earth. So when we ask, why might we be alone, we're really asking, how many planets out there have all the specific conditions that allowed life to develop here? And the answer is starting to look like not many. Let's move on to plate tectonics, because this might be the most underappreciated requirement for long-term habitability. Earth is the only planet in the solar system with active plate tectonics. Our outer shell, the lithosphere, is broken into several large plates that drift around on the underlying semi-molten asthenosphere, moving at rates of a few centimeters per year. Where plates collide, one can be forced beneath the other in a process called subduction, creating deep ocean trenches and volcanic mountain ranges. Where plates pull apart, new crust is formed from upwelling magma, creating mid-ocean ridges. This constant churning of the crust is essential for long-term climate stability through something called the carbon cycle. Here's how it works. Carbon dioxide in the atmosphere dissolves in rainwater, forming weak carbonic acid. This acid weathers rocks on the continents, breaking down silicate minerals and releasing calcium and bicarbonate ions that wash into the ocean. Marine organisms use these ions to build shells of calcium carbonate. When these organisms die, their shells sink to the ocean floor, forming layers of limestone. Over millions of years, plate tectonics drags this limestone down into the mantle through subduction zones. Deep underground, the limestone is heated, releasing the carbon dioxide back into the atmosphere through volcanic eruptions. This completes the cycle. The carbon cycle acts as a planetary thermostat. If Earth gets too cold, There's less rainfall and less weathering, so carbon dioxide builds up in the atmosphere, enhancing the greenhouse effect and warming the planet. If Earth gets too hot, there's more rainfall and more weathering, so carbon dioxide is removed from the atmosphere faster than it's replenished, cooling the planet. This feedback mechanism has kept Earth's surface temperature within a habitable range for billions of years, even as the Sun's output has increased by about 30% over that time. Without plate tectonics, without the carbon cycle, Earth's climate would have spun out of control long ago. We might have ended up like Venus, with a runaway greenhouse effect and surface temperatures above 450 degrees Celsius. Or we might have frozen solid like Mars. Plate tectonics requires a specific set of conditions. You need a rocky planet with a hot interior to drive mantle convection. You need water to lubricate the subduction process, weakening the crust enough that it can be dragged down into the mantle. You need the right crustal thickness and composition. Venus, which is nearly Earth's twin in size and probably has a hot interior, doesn't have plate tectonics. Its crust appears to be too thick and dry. Mars is too small and has cooled too much for plate tectonics. Earth is the only planet we know of with this crucial climate regulation mechanism. Lucky. Again. Now we come to one of the most dangerous periods in Earth's history, the Late Heavy Bombardment. About 4 billion years ago, roughly 500 million years after the solar system formed, something catastrophic happened. The inner solar system was suddenly bombarded by an enormous number of asteroids and comets. The lunar surface, which preserves a record of this period, shows a spike in large impact craters all dating to the same relatively short window of time. Earth, with its larger cross-section and stronger gravity, would have been hit even harder. Some estimates suggest that the late heavy bombardment delivered tens of thousands of impact events large enough to vaporize parts of the oceans. We're not entirely sure what triggered the late heavy bombardment. The leading hypothesis, called the Nice model, named after the French city where it was developed, suggests that Jupiter and Saturn were once in a different configuration, with their orbital periods nearly in resonance. Gravitational interactions between them caused their orbits to gradually migrate until they reached a critical point where the resonance broke, causing their orbits to suddenly shift. This shift destabilized the orbits of countless small bodies in the outer solar system, sending them careening inward. The bombardment eventually tapered off as the giant planets settled into their current stable orbits, and the supply of projectiles was exhausted. But for several 100 million years, Earth was being pummeled. Each large impact would have released enough energy to sterilize the surface, boiling the oceans and filling the atmosphere with vaporized rock. Any life that had emerged during this period would have been repeatedly exterminated, with only the hardiest organisms, probably thermophilic bacteria living deep underground or in hydrothermal vents, surviving to repopulate the planet after each impact. The late heavy bombardment finally ended about 3.8 billion years ago. The oldest undisputed evidence of life on Earth dates to about 3.5 billion years ago. Fossil stromatolites, layered structures built by microbial mats. But there are hints, controversial and disputed, that life might have existed even earlier, perhaps as far back as 4.1 billion years ago, based on isotopic signatures in ancient zircon crystals. If life did emerge that early, it would have survived the late heavy bombardment, possibly by retreating to deep subsurface environments. The late heavy bombardment represents a narrow window of opportunity. If you arrive at a solar system too early before the bombardment, any life that emerges will be sterilized. If you arrive too late, after the bombardment, you've missed out on hundreds of millions of years of potential evolution. Earth threaded that needle. Life emerged early enough to take advantage of the full span of geological time, but late enough to survive the worst of the bombardment. Or perhaps life emerged multiple times and was repeatedly sterilized until the bombardment finally ended. Either way, lucky timing. But surviving the late heavy bombardment was just the beginning. About 2.4 billion years ago, life on Earth nearly destroyed itself in what's known as the Great Oxidation Event. For the first 2 billion years of life's existence, Earth's atmosphere contained almost no free oxygen. Early life was anaerobic, living in environments where oxygen was absent or present only in trace amounts. Then, about 3 billion years ago, a group of bacteria called cyanobacteria evolved the ability to perform oxygenic photosynthesis, using sunlight to split water molecules and release oxygen as a waste product. At first, this oxygen didn't accumulate in the atmosphere. It reacted with dissolved iron in the oceans, forming rust that settled to the ocean floor. These banded iron formations are visible today in ancient rock layers. But eventually, after hundreds of millions of years, the oceans ran out of dissolved iron. The oxygen started bubbling out into the atmosphere. To most life on Earth at the time, oxygen was a deadly poison. It's a highly reactive molecule that damages cellular components. The rise of atmospheric oxygen triggered a mass extinction event, wiping out most anaerobic species. This is sometimes called the oxygen catastrophe, and it nearly ended the story of life on Earth right there. But some organisms adapted. They evolved biochemical pathways to safely handle oxygen and eventually to use it. Aerobic respiration, using oxygen to efficiently extract energy from organic molecules, became the dominant metabolism. Complex cells, eukaryotes, arose from a symbiosis between an anaerobic cell and an aerobic bacterium. That captured bacterium became the mitochondrion, the powerhouse of the cell, present in every complex organism alive today. Without the Great Oxidation Event, without the evolution of organisms capable of surviving in an oxygenated atmosphere, life on Earth would have remained simple. Multicellular organisms require large amounts of energy, and only aerobic metabolism can provide that energy efficiently. But the Great Oxidation Event was a close call. If cyanobacteria had never evolved, or if no organisms had been able to adapt to oxygen, Earth would remain a planet of microbial mats. The fact that life not only survived this self-inflicted catastrophe, but turned it into an opportunity. That's a filter that many planets might not pass. And then, about 700 million years ago, Earth nearly froze solid. Multiple times. These are called snowball Earth events, periods when glaciers extended from the poles all the way to the equator, covering the entire planet in ice kilometers thick. We know these events happened because we find glacial deposits, rocks that were clearly transported and deposited by glaciers, in what were tropical latitudes at the time. The exact trigger for snowball Earth events is still debated, but it probably involved a combination of factors. Continental drift brought large land masses into tropical latitudes where they experienced heavy rainfall and intense weathering, drawing down atmospheric carbon dioxide levels. With less carbon dioxide, the greenhouse effect weakened and temperatures dropped. Ice began forming at the poles, and here's where a dangerous feedback loop kicked in. Ice reflects sunlight back into space, far more effectively than open ocean or land. As more ice forms, less sunlight is absorbed, causing further cooling, which causes more ice to form, and so on. This runaway ice albedo feedback can, under the right conditions, lead to a completely frozen planet. Once Earth was in this frozen state, it should have been permanent. With the oceans covered in ice, there was no evaporation, no rain, no weathering, no way to remove carbon dioxide from the atmosphere. But there was still a way to add it. Volcanoes. Even with the surface frozen, plate tectonics continued. Volcanic eruptions kept pumping carbon dioxide into the atmosphere, and with no weathering to remove it, The concentration slowly built up over millions of years. Eventually, after perhaps 10 million years, the carbon dioxide levels got high enough that the greenhouse effect overwhelmed the ice albedo feedback. Temperatures rose. The ice began to melt. Once melting started, the feedback ran in reverse. Less ice meant more sunlight absorbed, which meant faster melting. Earth thawed in a geological blink of an eye, perhaps just a few thousand years. But during those millions of years of deep freeze, life hung on by a thread. The only photosynthetic organisms that could survive were those near hydrothermal vents or in thin meltwater zones, where volcanic heat or geothermal activity created small ice-free refuges. If Earth had frozen just a bit harder, if volcanic outgassing had been just slightly weaker, we might never have thawed out. Mars, after all, is frozen and has stayed frozen. The fact that Earth experienced multiple snowball events and recovered from all of them is remarkable. And some scientists argue that these near-death experiences might have actually accelerated evolution. The extreme environmental stress might have driven rapid adaptation. The sudden appearance of complex multicellular animals in the fossil record, the Cambrian explosion, occurred not long after the last snowball Earth event ended, about 540 million years ago. For 3 billion years, life on Earth remained mostly microbial. Then, in a geological instant, the oceans filled with a bewildering diversity of complex animals: trilobites, arthropods with jointed legs and complex eyes, Anomalocaris, a meter-long apex predator, Hallucigenia, a creature so bizarre that paleontologists initially couldn't figure out which end was the head. The Cambrian explosion is one of the most profound mysteries in evolutionary biology. Why did it take so long? What finally triggered the rapid diversification of animal life? We don't have definitive answers, but oxygen levels crossing a critical threshold probably played a role. So did the evolution of predation, which drove an evolutionary arms race, with prey developing shells and armor and predators developing better sensory systems and mobility. But the timing remains puzzling. If you were an alien astronomer observing Earth from a distant star system, for the first 4 billion years you would have seen no signs of complex life. Just a blue-green planet with microbial mats. Only in the last half-billion years, the most recent 11% of Earth's history, would you have seen anything more. This raises an uncomfortable question. How many planets out there have life? Simple microbial life, but never develop anything complex. How many planets remain stuck in the microbial stage for their entire habitable lifetime? Because Earth very nearly became one of them. Let's talk about intelligence, because even if you manage to get through all the planetary filters we just discussed, even if you end up with a world teeming with complex multicellular life, that still doesn't get you to a civilization capable of building radio telescopes and contemplating the cosmos. Intelligence, the kind of intelligence that leads to technology and science and philosophy, is not an inevitable outcome of evolution. It's not even a particularly common one. In fact, on Earth, it's only happened once. Think about that for a moment. Life has existed on this planet for at least 3.5 billion years. During that time, evolution has explored an almost incomprehensible variety of survival strategies. There are organisms that can survive in boiling water and organisms that can survive frozen in ice for thousands of years. There are organisms that see in ultraviolet and organisms that navigate by magnetic fields. There are organisms that can regenerate entire bodies from tiny fragments and organisms that essentially never age. Evolution has produced photosynthesis, echolocation, bioluminescence, metamorphosis, and countless other remarkable adaptations. But in 3.5 billion years, across billions of species that have existed at various times, intelligence of the human variety has evolved exactly once. Not twice, not a dozen times. Once. This should give us pause. If intelligence were an obvious advantage, if it were a natural endpoint of evolution, we'd expect to see it arise multiple times independently, the way we see eyes evolving independently dozens of times across different lineages. But we don't. The evolutionary biologist Stephen Jay Gould famously argued that if you could rewind the tape of evolution and play it again, you'd get a completely different outcome. The specific sequence of events that led to humans, the particular environmental pressures and random mutations and lucky breaks were so contingent, so dependent on historical accidents that they would almost certainly not repeat. Intelligence might be one of those historical accidents. To understand why, we need to look at what evolution actually optimizes for. And here's the thing. Evolution doesn't optimize for intelligence. It doesn't optimize for consciousness or curiosity or technological capability. Evolution optimizes for reproductive success. That's it. Whatever traits allow an organism to produce the most surviving offspring in its particular environment, those are the traits that get selected for. Intelligence is expensive. The human brain represents about 2% of body mass, but consumes about 20% of the body's energy at rest. That's an enormous metabolic cost. For most organisms, in most environments, that cost doesn't pay off. A larger brain doesn't help a tree reproduce more effectively. It doesn't help a jellyfish catch more prey. It doesn't help a bacterium survive in extreme conditions. For the vast majority of life on Earth, throughout the vast majority of Earth's history, intelligence has been irrelevant to reproductive success. In fact, by some measures, the most successful organisms on the planet are the least intelligent. Bacteria have been around for 3.5 billion years. They exist in every environment on Earth, from the upper atmosphere to deep within the Earth's crust. They outnumber all other forms of life combined. Their total biomass exceeds that of all plants and animals. If the goal is simply to exist and reproduce, bacteria have absolutely nailed it. They don't need big brains to do that. Insects are another wildly successful group. There are more species of beetles alone than there are species of all vertebrates combined. Ants outweigh all humans combined. Insects have colonized nearly every terrestrial habitat. They've been around for 400 million years and have survived multiple mass extinctions that wiped out larger, more complex organisms. They accomplish all of this with nervous systems that contain fewer than 1 million neurons. A honeybee has about 1 million neurons. A human has 86 billion. That's nearly a 100,000-fold difference in computational capacity. And yet, measured by evolutionary success, by sheer numbers and geographic distribution and longevity, bees are doing just fine. They don't need to be smarter. So why did humans become intelligent? What were the specific selection pressures that made our particular kind of intelligence adaptive? The answer is complicated and still debated, but it seems to involve a unique combination of factors that may not occur often on other planets. It starts with our ancestors coming down from the trees. About 6 million years ago, in Africa, climate change was turning forests into grasslands. Some populations of apes adapted by becoming bipedal, walking upright on 2 legs. This freed up their hands, which could now be used for carrying food, wielding tools, and gesturing for communication. Bipedalism also made long-distance travel more efficient, allowing these early hominins to cover larger territories in search of food. Around 2.5 million years ago, the genus Homo appeared, distinguished by larger brains and the use of stone tools. The oldest known stone tools date back even further, to about 3.3 million years ago, but they become much more sophisticated with Homo habilis and Homo erectus. Tool use created a feedback loop. Better tools allowed access to more food, particularly nutrient-rich meat from scavenging and eventually hunting. More food, especially protein and fat, could support larger brains. Larger brains could design better tools. This feedback loop, This coevolution of brain size and tool complexity is one of the key drivers of human intelligence. But tool use alone doesn't explain it. Many animals use tools. Sea otters use rocks to crack open shells. Crows fashion hooks from twigs to extract insects. Chimpanzees use sticks to fish for termites. None of these animals developed human-level intelligence. There's something else going on. That something else is social complexity. Humans are intensely social creatures. We live in large groups with complicated social hierarchies, alliances, rivalries, and relationships. Navigating this social landscape requires what psychologists call theory of mind, the ability to model what other individuals are thinking and feeling. You need to predict how others will react to your actions. You need to deceive and detect deception. You need to cooperate but also compete. You need to maintain your reputation. This cognitive arms race, trying to outsmart other members of your own species, is incredibly demanding. Some researchers argue that the primary driver of human intelligence wasn't environmental challenges like hunting or tool use, but social challenges. The smartest individuals, the ones who could best navigate complex social dynamics, had more allies, better access to resources, and more reproductive opportunities. Their genes spread. This is called the social brain hypothesis, and it's supported by comparative studies showing that across primates, brain size correlates more strongly with social group size than with ecological factors. Language was both a product and an amplifier of this social intelligence. The ability to communicate complex ideas, to share information about past events and future plans, to coordinate group activities, to teach skills to offspring, all of this made already intelligent hominins vastly more capable. Language allows culture to accumulate. Each generation can build on the knowledge of previous generations rather than starting from scratch. This cumulative culture, more than raw intelligence, is what separates humans from other animals. A lone human raised in isolation would not invent agriculture or metallurgy or mathematics. Those achievements required thousands of generations of accumulated knowledge, passed down through language and teaching. So, human intelligence required a very specific set of circumstances. We needed to be arboreal ancestors who came down from the trees. We needed climate change that favored bipedalism. We needed hands freed up for tool use. We needed social groups large enough to drive cognitive arms races. We needed language to enable cumulative culture. We needed an environment that made the metabolic cost of large brains worth paying. How often does that specific combination of factors occur? Let's look at other lineages that seem intelligent and ask whether they could have developed technological civilizations. Dolphins and whales are frequently cited as examples of intelligent non-human animals. Bottlenose dolphins have brains larger than humans in absolute terms. They have complex social structures. They appear to have individual names. They can recognize themselves in mirrors, suggesting self-awareness. Orcas have distinct cultural traditions, different hunting techniques passed down through generations. If we're looking for intelligent life in Earth's oceans, cetaceans are the obvious candidates. But here's the problem. Dolphins and whales live in water. Water is wonderful for many things. It's the medium in which life first evolved. It provides buoyancy, making it easy to grow large. It moderates temperature. But water makes it essentially impossible to develop technology. You can't make fire underwater. Without fire, you can't smelt metals. Without metals, you can't make complex tools. Without complex tools, you can't build cities or machines or electronics. A dolphin could be as intelligent as a human, could understand abstract mathematics and have rich inner emotional lives, and it would still never build a radio telescope. The environment simply doesn't allow it. This is a crucial filter. Intelligence alone isn't enough. You need intelligence to arise in an environment where that intelligence can be expressed technologically. Terrestrial environments with access to fire are essentially required. That rules out all aquatic life. What about other terrestrial animals? Elephants have large brains, exhibit complex social behavior, use tools, and show signs of mourning their dead. But elephants are quadrupeds. All four of their limbs are dedicated to locomotion. Their trunk is incredibly dexterous and they do use it for manipulation, but it's not as versatile as a pair of hands. More importantly, elephants are too large. An elephant can't sit at a workbench and assemble intricate devices. The square-cube law works against them. As organisms get larger, their strength increases with the square of their linear dimensions, but their mass increases with the cube. This means larger animals have a harder time supporting their own weight and require proportionally thicker limbs. Elephants are already pushing the limits of how large a land animal can be. They're not going to develop fine motor control for precision manufacturing. Octopuses are another frequently mentioned candidate for intelligence. They have large brains relative to their body size. They can solve puzzles. They can use tools. And they're masters of camouflage, able to change their skin color and texture in milliseconds to match their surroundings. But octopuses have several problems. First, they're solitary. Most species only interact with other octopuses during mating. There's no social structure to drive the cognitive arms race that helped develop human intelligence. Second, they're short-lived. Most octopus species live only 1 to 2 years. They don't have time to accumulate knowledge or develop culture. Third, and most fatally, they live underwater. Same problem as dolphins. No fire, no metallurgy, no technology. Birds, particularly corvids like crows and ravens, are remarkably intelligent. They can solve multi-step puzzles, use tools, recognize individual human faces, and even hold grudges. But birds are limited by their need to fly. Flight requires minimizing weight, which means small bodies and small brains. The largest brain that can fit in a flying bird's head is much smaller than a primate brain. Flightless birds like parrots can have larger brains relative to body size, and indeed parrots are among the most intelligent birds, but they still lack the manipulative appendages needed for fine tool use. Their feet are designed for perching, not precision grip. This brings us to a crucial point about the contingency of human intelligence. We're primates. Primates have grasping hands with opposable thumbs, a legacy of our arboreal ancestry. Tree dwelling requires sophisticated three-dimensional spatial reasoning and the ability to grip branches. When some primates moved to the ground, we already had the manipulative appendages needed for tool use. If primates had never evolved, if mammals had taken a different evolutionary path, it's not clear that any other lineage would have developed the combination of intelligence and manipulative ability needed for technology. Let's do a thought experiment. Suppose a giant asteroid hadn't hit Earth 66 million years ago. The dinosaurs would not have gone extinct. Mammals, which at the time were mostly small nocturnal creatures, would not have diversified and grown large. Primates would never have evolved. Would dinosaurs have eventually evolved intelligence? They had plenty of time to do so. Dinosaurs ruled the Earth for about 165 million years, from the late Triassic to the end of the Cretaceous. That's far longer than mammals have been dominant. During that immense span of time, dinosaurs evolved into an incredible diversity of forms. Gigantic sauropods weighing 80 tons, armored ankylosaurs, swift raptors with sickle-shaped claws, pterosaurs that took to the air. But none of them developed large brains. None of them showed signs of sophisticated tool use or culture. The smartest dinosaurs were probably the troodontids, small raptor-like theropods with relatively large brains and forward-facing eyes suggesting good depth perception. Some paleontologists have speculated about what might have happened if troodontids had continued to evolve. Could they have eventually become intelligent, tool-using species? We'll never know, because they went extinct along with all other non-avian dinosaurs. But they had tens of millions of years to become intelligent, and they didn't. This suggests that whatever selection pressures drove human intelligence are not universal, not inevitable outcomes of evolution. Dinosaur brains were optimized for different things: acute vision, precise coordination for hunting, navigating three-dimensional space in flight, but not abstract reasoning, not tool use, not language. After the dinosaur extinction, mammals radiated into the niches left vacant. Within 10 million years, mammals had diversified into most of the major groups we see today. Primates appeared about 55 million years ago. The first hominins, our direct ancestors, appeared about 6 million years ago. Humans with modern brain sizes appeared less than 300,000 years ago. Behaviorally, modern humans, with art and complex language and sophisticated tools, appeared less than 100,000 years ago. On a planet that's 4.5 billion years old, where life has existed for 3.5 billion years, humans are a very recent development. We showed up in the last 0.02% of Earth's history. If you compressed Earth's entire history into a single year, with the planet forming on January 1st, life would appear in late March. Complex, multicellular life wouldn't show up until mid-November. Dinosaurs would appear in mid-December, and humans wouldn't arrive until 11:58 p.m. on December 31st. Civilization, agriculture, cities, writing would all happen in the last few seconds before midnight. This raises a troubling question. If intelligence is so advantageous, why did it take so long to evolve? 3.5 billion years is an enormous amount of time. Evolution can work incredibly fast when there's strong selection pressure. Bacteria can evolve resistance to antibiotics in a matter of years. Darwin's finches evolved different beak shapes in response to drought conditions within decades. Populations of fish have evolved into distinct species within a few thousand years, when separated into different lakes. Evolution has no shortage of time or raw material to work with. The fact that intelligence took billions of years to evolve suggests that either the selection pressures favoring it are extremely rare and specific, or there are barriers that make intelligence difficult to evolve, even when it would be advantageous. One barrier might be energy. Brains are metabolically expensive. A large brain requires a nutrient-rich diet to support its energy demands. Herbivores who eat plant matter that's relatively low in calories and requires extensive digestion typically can't afford large brains. Carnivores and omnivores with access to energy-dense food are better positioned to evolve intelligence. Most of the intelligent animals we mentioned, primates, dolphins, elephants, crows, are omnivores or carnivores. But even then, you need a reliable food supply. If you're spending all your time and energy just finding enough food to survive, you can't afford to divert 20% of your metabolism to running a big brain. This might explain why intelligence evolved in social species. Social groups can cooperate to acquire food more efficiently. They can defend food sources from competitors. They can share information about where food is located. Sociality makes the high cost of intelligence more affordable. Another barrier might be parental care. Large brains take a long time to develop. Human infants are born with brains that are only about 25% of adult size. Our brains continue growing and developing for years after birth. This extended development period requires intensive parental care. Human children are dependent on adults for food and protection much longer than the offspring of most other animals. This extended childhood is necessary for our brains to develop fully, but it's also risky. It means each offspring requires a huge investment of time and resources. For most animals, that investment isn't worth it. They're better off producing many offspring quickly with minimal parental care, accepting that most will die, but some will survive. humans take the opposite strategy. Few offspring, massive investment in each one. This K-selection strategy only makes sense in specific environmental contexts, usually stable environments where adult survival rates are high. Yet another barrier might be the absence of the right kind of competition. Remember, intelligence in humans seems to have been driven largely by social competition, by the need to navigate complex social hierarchies. That kind of competition requires living in stable groups large enough to have real social structure, but not so large that individuals can't track who's who. It requires a social system where individual reputation matters, where cooperation is rewarded, and where cheaters can be identified and punished. Many social species don't have this. Ants live in huge colonies, but they don't have individual identities or reputations. Each ant is essentially interchangeable. There's no selection pressure for individual intelligence. Conversely, some intelligent animals like octopuses are solitary. There's no social complexity to navigate. Humans hit a sweet spot. Groups large enough for complex social dynamics, but small enough for individual relationships to matter. How often does that occur? Looking across the animal kingdom, most species are either solitary, live in small family groups, or live in huge colonies where individuals don't matter. The middle ground is rarer than you might think. And even when all the conditions are right, even when you have a social omnivore with manipulative appendages living in an environment that favors large brains, intelligence still isn't guaranteed. Consider Neanderthals. They were closely related to modern humans, close enough that we interbred with them. They had brains slightly larger than ours. They used sophisticated tools, controlled fire, buried their dead, and possibly had language. By any reasonable definition, they were intelligent. And yet they went extinct about 40,000 years ago, possibly outcompeted by Homo sapiens, possibly victims of climate change, or possibly just bad luck. Intelligence didn't save them. Or consider Homo erectus, which existed for nearly 2 million years, far longer than Homo sapiens has existed so far. Homo erectus had brains about 70% the size of modern humans, used stone tools, controlled fire, and spread from Africa across Asia. They were successful by evolutionary standards, persisting through multiple glacial cycles. But they never developed agriculture or civilization. They remained hunter-gatherers with simple stone tools for their entire existence. What was the difference between Homo erectus and Homo sapiens? What made us take the final steps toward civilization when they didn't? We don't know for certain. It might have been biological, some further increase in brain size or cognitive capability. It might have been cultural, some innovation in language or social organization that allowed knowledge to accumulate more effectively. It might have been environmental, a lucky break in climate that allowed population densities to increase to the point where specialization and trade became possible. Or it might have just been luck. The point is, even within the genus Homo, even among species that were already intelligent tool users, the jump to technological civilization was not inevitable. It happened once, very recently, and it came close to not happening at all. During the Toba supereruption about 74,000 years ago, a volcanic event so massive it triggered a volcanic winter lasting years, the human population may have crashed to as few as a few thousand individuals. Genetic evidence suggests a severe population bottleneck around that time. We nearly went extinct. If that small surviving population had succumbed to starvation or disease or just bad luck, Earth would today be a planet with no technological civilization, no art, no science, no philosophy, despite having all the pieces in place for intelligence to evolve. This brings us to a deeply uncomfortable possibility. Maybe intelligence is not just rare, but freakishly, improbably, lottery winner rare. Maybe Earth isn't just lucky. Maybe Earth is the jackpot. When we look at the history of life on this planet, we see intelligence evolving exactly once, very recently, after 3.5 billion years of life existing without it, in a lineage that happened to have the right body plan due to an arboreal ancestry, that happened to experience the right environmental pressures due to climate change in Africa, that happened to develop language and cumulative culture through a series of fortunate accidents, and that came within a hair's breadth of going extinct multiple times. If you changed any one of a dozen factors along the way, we wouldn't be here. Rewind the tape and play it again, as Stephen Jay Gould suggested, and the odds of getting anything like humans seem vanishingly small. And here's the really terrifying part. Even if intelligence does evolve on another planet, even if some alien species manages to thread all the same needles we did, they still have to survive long enough to develop radio technology and become detectable. That's the subject of our next chapter, because the filters we've discussed so far, the planetary filters and the biological filters, might not be the deadliest ones. The deadliest filter might be the one that awaits any species that becomes technologically advanced, the filter we're approaching right now. For thousands of years, we believed we were the center of everything. Earth was the center of the universe. Then came the Copernican revolution. Nicolaus Copernicus demonstrated in 1543 that Earth orbits the Sun, not the other way around. We weren't the center of the universe, we were just another planet. Then we discovered that the Sun isn't the center of the universe either. It's just one star among hundreds of billions in the Milky Way galaxy, located out in the suburbs, about 2/3 of the way from the center to the edge. Nothing special about it. Then we discovered that the Milky Way isn't the center of the universe either. It's just one galaxy among trillions. Edwin Hubble proved in 1924 that the fuzzy nebulae we'd been seeing through telescopes were actually other galaxies, island universes in their own right, scattered throughout space as far as we could see. This progressive demotion is sometimes called the Copernican principle, or the principle of mediocrity. The idea is that there's nothing special about our location or our time or us. We're average, typical, mediocre. And from that principle, scientists extrapolated that life must be common. If we're not special, if Earth isn't special, then surely other planets must have developed life too. The universe must be teeming with it. SETI was founded on this assumption. The Drake equation was built on it. Carl Sagan spent his career promoting it. But what if the Copernican principle is wrong? Not wrong in the sense that Earth is the center of the universe, we're clearly not, but wrong in the sense that we're typical. What if we're not mediocre? What if we're extraordinary? What if the Great Silence is telling us that conscious technological life is not common, not rare, but unique? That Earth is the only planet in the observable universe that has produced a civilization capable of contemplating the stars. This possibility is sometimes called the rare Earth hypothesis, and it's fallen out of favor in recent decades, partly because it feels like a return to pre-Copernican anthropocentrism, putting humans back at the center of everything. But being unique doesn't mean being central. It doesn't mean the universe was created for us or that we're the purpose of existence. It just means that the path from matter to mind is so narrow, so fraught with bottlenecks and filters and sheer bad luck that it almost never happens. We got lucky. Incredibly, improbably, lottery winner lucky. And the implications of that are staggering. If we're alone, then we're not just another species trying to survive on one planet among trillions. We're the custodians of something irreplaceable. We're the only instance in the entire observable universe of matter becoming aware of itself. The only place where the universe has developed eyes to see itself, a mind to understand itself. Every human being who has ever lived, every work of art ever created, every scientific discovery ever made, every moment of love or beauty or wonder, all of it exists in this one fragile bubble of consciousness surrounded by an ocean of lifeless matter stretching for billions of light years in every direction. If we destroy ourselves, if we fail to navigate the great filter ahead of us, we're not just ending human civilization. We're ending the only civilization. We're extinguishing the only light in an otherwise dark universe. The responsibility that comes with that realization is almost unbearable. It changes the moral calculus of everything we do. Existential risks, the things that could cause human extinction or permanent civilizational collapse, aren't just threats to us. They're threats to the universe's only chance at understanding itself. Climate change isn't just about preserving our quality of life. It's about ensuring that consciousness itself survives. The development of artificial intelligence isn't just about technological progress. It's about whether the only intelligent species in the universe will be succeeded by something else or will simply end. Nuclear weapons stockpiles aren't just a threat to human populations. They're a threat to the only populations anywhere. Every decision we make as a species takes on cosmic significance if we're alone. We can't afford to fail. There's no one else to carry the torch. There's no backup civilization waiting in the wings. If we go extinct, the universe returns to darkness for potentially the rest of its existence. Because even if life could evolve again elsewhere, it might take so long that the universe itself runs out of time. The universe won't be habitable forever. Stars are fueled by nuclear fusion, and they're burning through their fuel supply. The star formation rate in the universe has been declining for billions of years. We're already past peak star formation. In a few trillion years, all the star-forming gas will be used up, and no new stars will be born. Existing stars will burn out. The universe will gradually go dark. Long before that, in about 5 billion years, our own sun will exhaust its hydrogen fuel and expand into a red giant vaporizing Earth. Any descendants of humanity will need to have moved to other star systems by then. In about 4 billion years, even before the sun dies, the Andromeda Galaxy will collide with the Milky Way. The collision won't be violent in the sense of stars crashing into each other. Space is too empty for that. But the gravitational interactions will fling star systems around, possibly ejecting some from the merged galaxy entirely. Solar systems with planets in habitable zones might suddenly find themselves in much less hospitable environments. The window for life in the universe is finite. We might be living in that window right now. We might be the first and only species to evolve intelligence during the brief cosmic epoch, when the universe is old enough to have produced heavy elements and stable planetary systems, but young enough that stars are still shining and planets are still habitable. If we fail, if we don't make it through the next few centuries, the universe might never get another chance. Of course, we don't know for certain that we're alone. The universe is vast beyond human comprehension. The observable universe has a radius of about 46 billion light years. That's the distance light has been able to travel since the Big Bang, accounting for the expansion of space. Beyond that horizon, we can't see. There could be trillions of civilizations out there, but they're too far away for their light to have reached us yet. We'll never see them, never communicate with them, never know they exist. Even within the observable universe, even if we're not seeing any signs of alien civilizations now, that doesn't prove they're not out there. Maybe they're using communication, technologies we haven't invented yet. Maybe they're deliberately staying quiet, practicing what's sometimes called radio silence, for the same reasons some people think we should. Maybe they're so far away that their signals have attenuated below detectability. Maybe they exist, but at different times than us. The galaxy is billions of years old. A civilization could have risen and fallen 100 million years ago, leaving no trace we could detect today. Or a civilization might arise 100 million years from now, long after we're gone. Two ships passing in the night, never knowing the other existed. These are all possibilities, but they're starting to feel less like reasonable alternatives and more like hopeful excuses. We've been searching for 70 years. We've examined thousands of stars. We've looked for radio signals, optical signals, infrared signatures. We've searched for megastructures, signs of stellar engineering, industrial pollution in exoplanet atmospheres. We've found nothing. At some point, the absence of evidence starts to become evidence of absence. Let's assume for the rest of this discussion that we're genuinely biological beings living in base reality, confronting the genuine possibility that we might be alone. What should we do with that knowledge? How should it change our behavior? The immediate answer is that we need to take existential risks far more seriously than we currently do. Right now, human psychology is poorly calibrated for thinking about low-probability, high-consequence events. A 10% chance of human extinction sounds small. It sounds like something we can afford to ignore in favor of more immediate concerns. But if you were told you had a 10% chance of dying every time you got in a car, you would never drive. We need to treat existential risks with the seriousness they deserve, even when the probabilities seem small, because the consequences are literally as bad as they can possibly be. Climate change is the most pressing challenge on a short timescale because we're already locked into some warming and the effects are already being felt. We need to transition away from fossil fuels as quickly as possible. That means massive investment in renewable energy, nuclear power, energy storage, and carbon capture. It means redesigning cities and transportation systems. It means changing agricultural practices. It means international cooperation on a scale we've never achieved before. None of this is easy, but all of it is technically feasible with current technology. The barriers are political and economic, not physical. Whether we successfully address climate change will be one of the first major tests of whether humanity can coordinate to solve global problems. If we fail this test, it bodes poorly for our ability to handle the even harder challenges ahead. Artificial intelligence is the most pressing challenge on a medium timescale. We probably have a few decades before AGI, though it could be sooner. We need to use that time to solve the alignment problem, to figure out how to create systems that reliably do what we want them to do, even when they're smarter than us. This requires technical research into AI safety and alignment. It also requires slowing down the race to AGI so that safety research can keep pace with capabilities research. Right now, we're not doing that. AI development is a competitive free-for-all with minimal oversight or safety standards. We're sprinting toward AGI with our eyes closed, hoping we don't run off a cliff. Some researchers are calling for a pause in AI development until we have better safety frameworks in place. That's probably not going to happen because the economic and military incentives are too strong. But, at minimum, we need governments to start treating AI as the existential risk it is, and implementing regulations to ensure safety research is adequately funded and that systems aren't deployed prematurely. Nuclear weapons remain a persistent background threat. We've been lucky so far, but luck runs out. We need continued work on arms control, improved communication between nuclear powers, and eventual disarmament. Getting rid of nuclear weapons entirely is politically difficult because they serve as deterrents and symbols of national power. But the risks they pose, especially as more countries develop them and as delivery systems become faster and harder to defend against, are simply too high to tolerate indefinitely. If we do survive the next few centuries, if we make it through the Great Filter, what then? The long-term trajectory for humanity, assuming we're alone in the universe, is both exhilarating and sobering. We have the entire galaxy to explore and colonize. No one is going to stop us. There are no competing civilizations, no wars over resources or territory with alien species. It's all ours. We could spread to every habitable planet in the Milky Way. We could build habitats in space, O'Neill cylinders and Stanford Tori, artificial worlds with their own ecosystems. We could disassemble planets to build Dyson swarms, capturing all the energy output of stars. We could persist for trillions of years, long after Earth is gone, riding the slow decline of the universe toward heat death. The number of humans who could potentially exist in that future is staggering. If we colonize just the Milky Way, even with conservative assumptions about population density and available resources, you're talking about something like 10 to the power of 34 people who could live in the future. That's a 1 followed by 34 zeros. More people than have ever lived on Earth by a factor of 1 trillion. The moral weight of that potential future is almost impossible to comprehend. Every person alive today is responsible, in some small way, for whether that future happens or not. Some people find the prospect of being alone terrifying. The universe seems cold and empty. It makes our existence feel fragile and contingent. If we're the only ones, then we're also the only ones who can fail. There's a loneliness to it, the cosmic equivalent of realizing you're the last person on Earth. But there's another way to look at it. If we're alone, then every person matters more, not less. Every life has cosmic significance because conscious experience is so rare. Every act of kindness, every work of art, every scientific discovery, every moment of beauty or joy or connection, all of it is infinitely precious because it's happening in the only place in the universe where such things are possible. We're not insignificant specks in an uncaring cosmos. We're the part of the cosmos that cares. We're the universe experiencing itself, understanding itself, mattering to itself. And if we're the only ones doing that, then far from making us less important, it makes us the most important thing there is. The astrophysicist Carl Sagan, who spent much of his career searching for extraterrestrial intelligence, and who would probably be disappointed by the possibility that we're alone, nevertheless recognized the preciousness of what we have. He wrote about Earth as a pale blue dot, a tiny speck suspended in a sunbeam, and how all of human history has taken place on that speck. Every king and peasant, every saint and sinner, every young couple in love, every mother and father, hopeful child, inventor and explorer, every hero and coward, every creator and destroyer of civilization, lived on that mote of dust suspended in a sunbeam. Sagan meant that as a humbling observation, a reminder of our smallness. But it's also ennobling. All of that history, all of that experience, all of that meaning emerged from a single planet. And if we're alone, that's the only planet in the entire observable universe where anything like that has ever happened. We are the heirs to that history. We're the current instantiation of the universe's self-awareness. And the question facing us now is whether we can grow up fast enough to survive our own power. Whether we can develop the wisdom to wield technologies that could destroy us. Whether we can cooperate on a global scale to solve problems that threaten our existence. The stakes have never been higher. For most of human history, our mistakes were local. A civilization could collapse, but others would continue. A war could kill millions, but billions would survive. We couldn't threaten the entire species. That's no longer true. We now have technologies that could end everything. And we're developing more such technologies faster than we're developing the wisdom to control them. This is the test. This is the great filter. And we don't know if we're going to pass. I want to be clear about something. Nothing in this discussion is meant to be fatalistic. The fact that we face existential risks, that we might be approaching a great filter, doesn't mean we're doomed. It means we need to take these risks seriously. The future is not predetermined. We have agency. The decisions we make, individually and collectively, matter. If you're watching this, if you're one of the 8 billion people currently alive, you're living through the most consequential period in human history. The next few decades will likely determine whether humanity survives to become a spacefaring civilization or whether we join the Great Silence. another failed experiment in the universe's long history. That's not hyperbole. That's just an accurate assessment of where we are. If we survive the next few centuries, if we make it through the Great Filter, we'll have proven something profound. We'll have shown that intelligence can mature, that technological civilizations can navigate the dangers of their own power, that consciousness can persist in the universe not just as a brief flicker, but as an enduring presence. We could be the beginning of something vast, the seed from which a galaxy-spanning civilization grows, the ancestors that future humans look back on and say, "That's when it all began. That's when we decided to survive." Or we could be a cautionary tale, a dead civilization on a warming planet circling an ordinary star, another data point in the universe's statistics about how often intelligence arises and how often it fails. The universe has been silent for billions of years. It might stay silent forever. But for now, on one small planet orbiting an average star in an unremarkable galaxy, there's noise. There's music and laughter and argument. There's science and art and love. There's consciousness pondering its own existence. There's us. And the question we face, the only question that really matters, is whether we can keep that noise going. Whether we can survive our own adolescence as a species and grow into something worthy of the cosmic opportunity we've been given. I don't know the answer. Nobody does. We're writing it in real time. But I do know this. If we're alone in the universe, if consciousness exists only here, only now, only in us, then we owe it to the cosmos itself to try. Not to destroy ourselves would be the ultimate tragedy, not just for humanity, but for the universe, which would lose its only chance at self-reflection. So we keep searching the skies, even if they stay silent. We keep working on the problems that threaten us. We keep building, creating, exploring, learning. We keep trying to be worthy of this improbable gift of existence. Because maybe, just maybe, we're not alone. Maybe somewhere out there, on a planet orbiting another star, there's another civilization having this same conversation, confronting their own great filter, wondering if they're the only ones. And maybe, millions of years from now, when we've spread to the stars and they've spread to theirs, our descendants will meet their descendants in the space between galaxies, and they'll share their stories, and they'll realize they were never truly alone. But until that day comes, if it ever does, we act as if we're the only ones. We take responsibility for consciousness itself. We become the guardians of the cosmic flame. And we hope that when future generations look back at this moment, at this critical juncture in human history, they'll say we chose wisely, that we stepped back from the brink, that we grew up, that we survived. The universe is waiting to see what we do next. Let's not disappoint it. Sleep well.